The sky is not blue. It's mostly transparent air, which is, at best, the color of whatever light it scatters. Sure, it does scatter blue light more than red light. In fact, the higher the frequency of light, the more it gets scattered by the atmosphere. So ultraviolet scatters more than blue, which scatters more than green, more than yellow, more than red, more than infrared. But still, only a tiny bit of light scatters, while most of it goes straight through, which is, how the sun can light up the ground, why we can see the moon and stars through the atmosphere, etc. The sun itself actually emits a wide range of frequencies of light, and our human eyes perceive this particular combination as white or neutral in color. The vast majority of the sky appears bluish because sunlight that was trying to go somewhere else got scattered by the air and instead ended up in your eye. Bummer. It still has a wide range of frequencies in it, with slightly more blue than in white light, roughly the same amount of green, and less red. You can see a simple demonstration of this on a computer if I take a white background, add a bit of deep blue, and subtract a tiny bit of pure red. I get a nice sky color. And the reverse effect happens when you look near the sun. Light that was trying to get to your eyes gets scattered away, so the remaining light has a lot less blue and slightly more red, compared with white light, which is why the sun and sky directly around it appear yellowish during the day. At sunset, there's even more air for the light to scatter off of before it reaches you, hence the even richer oranges and reds. And of course you can do the computer demo again, this time subtracting pure blue and adding a little red. Voila, noontime sun. Subtract more blue and add even more red? Sunset orange. So the sky is not blue. It's a stage upon which all colors dance. Red colors tend to dance in straighter lines, green colors more randomly, and deep blue colors dance the most frenetically of all. Yet at some point, they all ultimately dance their way into your eyes, and my eyes, and to the earth and into space, so that everyone everywhere can appreciate the grand ballet of light. Gasoline has approximately 56 megajoules of chemical energy per liter, which is more energy than you get from exploding the same amount of TNT, and is enough to power a toaster for a full day. Cars work by burning gasoline to convert that chemical energy into the kinetic energy of motion of the car, though almost 80% of it is lost as heat in the engine. Still, 20% of 56 million joules is a lot of joules. To give a direct sense of gas to car conversion, it takes about 5 teaspoons of gas to accelerate a 2-ton car to 60 kilometers per hour, and about a third of a cup more for every additional minute you want to keep it going at that speed. That might not sound like a lot of fuel, but the energy of a car moving 60 kilometers per hour is equivalent to dropping an elephant, or stegosaurus, from the top of a 3-story building. And in order for the car to stop, all that energy has to go somewhere. If the brakes do the stopping, they dissipate the energy by heating up. Or in the case of a collision, energy is dissipated by the bending and crumpling of metal in the outer areas of the car. And just like how smooth braking is nicer than a quick, jerky stop, cars are carefully designed to crumple when they crash, in a way that lengthens the duration of the impact so that stopping requires less intense acceleration. Lots of acceleration over a very short time is not good for soft human brains and organs. However, people don't like driving cars with Pinocchio-length noses, so most cars only have around 50 centimeters of crushable space in which to dissipate the energy equivalent of our falling stegosaur. That means that while crumpling, they need to maintain a resistive force of about a quarter of the thrust of the Space Shuttle main engine. Over half of the controlled crumpling work is done by a pair of steel rails connecting the front bumper to the body, which bend and deform to absorb energy and slow the car. Most, and in ideal circumstances all, of the rest of the energy is absorbed by the deformation of other pieces of structural metal throughout the front of the car. This meticulously engineered destruction allows a crashing car to decelerate at a high, but reasonable and constant rate, just slightly over the acceleration experienced by fighter pilots or astronauts in centrifuge training. As comparison, if cars were super rigid, like they were before the 1950s, and didn't crumple, they would stop so fast that they would undergo acceleration 15 times what fighter pilots experience in training, which is definitely not good for your internal organs. Thankfully, engineers have learned to make cars with crunchy crumple zones surrounding a rigid safety cell, because fully rigid cars are not good for fighter pilots or anyone else. Except maybe robots.